Hi guys, welcome. Okay, so in today's lesson, we are going to start having a look in the study of multivariable functions. So what we're gonna do is we are going to lay down some definitions so that you may understand what we mean by multivariable functions. And today's lesson is mainly focused on knowing how to find the domains of such functions. You see? Okay, so let's begin. So what is a multivariable function? So a multivariable function is a function of the form f from R to N to R. So a multivariable function is just a function f which takes n tuples and makes that to a real number. So let me not use the word it is a function of the form, but to just say it is the function f is a function f which takes R to N to R. So remember, what exactly do we mean by R to N? So if you recall, R to N, it simply means the coordinate x1, x2, to xn with each xi an element of the real numbers. You see, so a multivariable function is a function which takes a tuple, and from that tuple, it maps it into a real number. So these are what we are going to look at today to try and see what we can do with these type of functions. So though now we have defined a multivariable function in general, today we are going to try and focus on looking at these functions in two-dimensional space. So the order of the tuple that each function can take, it is called the dimension of that function, you see. So if we have a function like this one, which takes in n a tuple or with n coordinates, then we say this is an n-dimensional function, like that. So we refer to that n as the dimension of the function. So what we're going to see now is what are examples of such functions that we refer to as multivariable functions. But in 2D, you can simply define a multivariable function. So in 2D, a multivariable function is just a function which takes R2 and returns a real number. You see. So examples of such function, we have f of xy is equal to 2x y cubed plus 4y to the power 4, like that. You see. So though on the right hand side it looks like you have an algebraic expression, you can see that if you are to find maybe a function of 1, what you get is just 2 plus 4, which is 6. So we see that this tuple that we have here has just been mapped to a single real number, like that. So that's what multivariable functions are. So also we have them in three-dimensional form. In three-dimensional form, it is defined as the function which takes R cubed and it maps it to R. And an example of such a function is a function f of x, y, z, which is defined as x cubed plus y cubed plus z cubed. So all these are different examples of what are known as multivariable functions in two-dimensional and three-dimensional space, you see. So every time when we talk about multivariables, this is what we mean when we say a function is a multivariable. So being multi, it is something which is associated with the argument. What is the structure of the element that it takes as the domain. So if a function takes coordinates as its arguments, then that's what we mean by multivariable functions. So today our main focus mostly will be on two-dimensional functions, and but whatever we're going to discuss, it also applies similarly to three-dimensional functions. So you can just use the information of today's lesson to even expand to three-dimensional functions like that. Okay, so now we have understood the definition of what we mean by multivariable. Now it's time to start a discussion on today of what we want to specifically look at today, which is the domain of f R2 to R. So now let's understand a thing or two about the domains of two-dimensional functions. You see that? Because most questions that you are more likely to get in test or exams, they will be just about you having to find the domain of these functions and also to sketch these domains. So first we have to understand geometrically what is the domain of a two-dimensional multivariable function like that. You see that? So we know that the domain of f, which is a function from real numbers to real numbers, is a subset of the real line. You see that? So we know that every time when you have a function which is a univariable, we understand geometrically that for such functions, if you are asked to find the domain is always a subsection of the real line. You see that? So it always represents a certain interval or a union of interval that are just pieces of the real line. So now what we want to understand is, in the same analogy, what is the domain of a two-dimensional function, of a two-dimensional scalar function like the one that we are already discussing here geometrically. You see? Yes. So, and for a 2D function, f, which takes R2 and maps it to R, the domain is always an area or a union of areas in the R2 plane. You see that? So geometrically, when we have a two-dimensional function, one which takes two tuples and makes them to a single number, if you're asked to find the domain, first you must understand the nature of the domain that you're trying to find. So the domain of functions like these, they are always represented as areas in the R2 plane. So what we mean by that is, if you have some function f which maps R2 to R, then what you should know is that the domain of such a function is always some area which resides in the R2 plane space. You see, so it can be the area that is inside here, or it can even represent the area which is outside this region. But what you should just know is that the domain of any R2 function is always like that. So what we can say in other words is that the domain of f, where f is just that function that we have already stated, which takes an R2 coordinate, then it is always a subspace or a subset of R2. You see that? So, and it is always such that it is made up of coordinates x, y, all elements of R2, such that some property holds true, like that. So this is the structure of the domains of functions that are two-dimensional in terms of order. like that. So yeah, these are some basic things that you should know, because if you're asked to find the domain and you don't know the nature of the domain that you're trying to find, these problems can be quite difficult to solve. So at least you must at least have some intuition to say, okay, what exactly am I looking for here? So every time when you are finding or looking for the domain of a multivariable function, you are looking for a certain region. So if it's a 2-dimension, the region is always an area in the xy coordinate. You see that? If you are to take these to higher dimensions like 3-dimensional space, then this thing generalizes to become a volume. So if you are looking for the domain of a 3-dimensional multivariable function, then that domain has to be some volume in 3D space. So it always generalizes to higher orders going like that. So you'll find that when you go to high orders like n orders, you start getting things like hypervolumes, which become the domains of those functions. But now we won't look at finding domains of such complicated functions which live outside higher spaces like 4 and upwards. We'll just restrict ourselves to look at cases where we only deal with 2-dimensional functions and also 3-dimensional functions, you see. So next, now what we're going to do now is we are going to see now how exactly then do we go about finding the domains of such functions. So we are going to do that by looking at different examples. So what you have to do is to pay attention to the thought process that is done behind establishing the domains of such functions. So to begin, we have the following example. So the example that we have is as follows. So what we are asked is we are given a function f of xy, which is defined to be x ln of y squared minus x. So the question that we are asked is find the domain of f and sketch it. So this is what we are asked. So we are given this function and they say find the domain of this function and sketch that domain. So how can one go about solving a problem like this one? So to solve a problem like this one, this is how we proceed. So at first, you have to study the nature of the function itself, and you see if there is the presence of functions that we are familiar with, which we know that they have certain restrictions that they're always associated with. Like for example, if we are to consider our function f of xy, which is given as x ln of y squared minus x. So one thing that we can see immediately is the presence of the logarithmic function. So the logarithmic function can be our guide as to how we are going to find this domain. So to find the domain, we have to ask ourselves, all these functions that we see which make up the function fxy, do they have restrictions? So already we have a product of two functions and x and the natural log of y squared minus x. So x is a polynomial, and we know that polynomials, they do not have any restriction in them. They can take anything. For everything that you give them, they give you an output. But that's not the case for the logarithm. For the logarithm, we know that if you are someone who is expecting an output, you must always put something which is positive. And by positive, we mean strictly positive, meaning you must never put something like 0. So 0 can never give you anything, or anything less than 0 can never give you anything for a natural log. So a natural log can only give you outputs if you take something which is strictly greater than 0. You see that? So from this now we can therefore proceed as follows. So we know that y minus x must always be greater than 0, always. You see that? So this implies y squared must be greater than x all the time. So since this is the only restriction that we have, it means therefore that the domain of f that we're looking for, it is all the set of coordinates which resides in R2 such that y squared is greater than x always, like that. So that's all that we need. So this is the domain that we are looking for. But now we are not asked to just find it, but we are told also to find it and then sketch it. So how can we go about sketching this kind of domain? So to sketch this kind of domain, what we do is first we construct our two-dimensional space, the xy plane, and then what we do now is we put the restriction inside. So what is the restriction? We are told that we can take anything, but anything that we can take must be such that y squared is greater than x. So every time when you want to plot a domain of a particular multivariable function, the first thing is you must sketch the condition itself. So which means first you must sketch that condition and show how it looks inside the Cartesian plane. So how do we sketch that? So to sketch that, the first question that we can look at is, suppose we just look at the equality, you see. So let's consider instead y squared is equals to x. So if now you consider y squared equals to x, which curve possesses all those points that satisfy this condition? So I think we know already that all points where y squared equals to x, they lie along a curve which behaves like that. You see, so y is equals to x squared consists of all points which lie along this path. But now, for us, we are told that we don't need points where y squared is equals to x, but we need the points where y squared is above x, which means now we have to ask ourselves, where do all such points live? You see, where do all these points live? Do they live on the interior of this boundary? Because this boundary, remember, it goes all the way to infinity, like that. It goes all the way to infinity. So the question now that we should ask ourselves is, the points that we are looking for that satisfy this condition, do they live on the outward of this boundary, that is here, 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 or do they live in the interior, that is here, 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 here? You see. So this is something at times that can be hard to figure out, but we can just figure out it nicely by checking maybe a few points that lie outside the region and seeing if they do satisfy that condition. So if you are to take a point that lie here, 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 sorry. So if you have to take a few points which lie here, 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 and random here, 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 you will see that all the points that lie within this interior, they will fail to hold true for that inequality. So all the points that you are going to observe that are going to hold true for that inequality are all the points that lie outside that region. So all points that lie outside that region are the ones that are going to satisfy your inequality. If you are to play around with taking different values inside and outside and seeing if your inequality was true. So you will see that yes, all such values that we need, they reside in this region. So which shows that this is the domain that we are looking for. So even here along the x-axis, everything still holds perfectly fine. So this forms the domain of our function. So this is the domain of f. So this whole shaded region represents the domain of f, like that, you see. So we don't need anything inside here and inside here. Everything that we need lies outside of that curve. So this is simple how you find the domains of all these functions. So the next thing that we want now is to look at another example. So the other example that we have, it goes as follows. So we are given a function g of xy, which is defined as root of 9 minus x squared minus y squared. And we are asked to find also the domain. So determine the domain of G and sketch it. You see, so we want to determine the domain of this G and then sketch it. So how can we go about finding the domain of this function? So to find the domain, this is how we proceed. First, we look at the nature of functions that we have. So we see already there is the presence of a square root in our problem. And we know that a square root comes with restriction. So what are restrictions of the square root? The restrictions of the square root are that every argument that you give to the square root must be non-negative, meaning you must only provide things that start from 0 and upwards. Anything which is less than 0 will not give you output. So that's our starting point. So we know that 9 minus x squared minus y squared must always be greater than 0, always. You see, so this thing must always be greater than 0. So this implies what? So if we take the other terms there, we get x squared plus y squared, a is less than equal to 9. You see, so therefore the domain that we're looking for of f is just the set of all points x, y, elements of r squared, such that x squared plus y squared is less than or equal to 9. Like that. So this is what we are looking for. But now how do we sketch this domain that we have here? How do we sketch it? So to sketch this domain, you know that you first have to sketch the restriction itself. So how will this restriction look like in a Cartesian plane? So if you look closely, you can see that this restriction is a circle whose radius is 3. So we have a circle, and since it says greater or equal to, it means the circumference also is required as part of the domain. So we draw it in bold line. So here we have 3 minus 3 minus 3, 3. You see, so it shows that here now we need all points where x squared plus y squared is less than 9. So in other words, we just need all points that reside inside this circle. So it means the domain that we're looking for is everything that lies in the interior of this circle, like this. So everything that lies inside the interior is the domain of f that you are looking for. So this is how easily you can find domains of functions and sketch them. You see, so all these are familiar problems that are quite common when it comes to these things. So it's good to find similar problems and practice them and apply all the techniques that you are using here to sketch these domains. You see. Then the next one that we have, it goes as follows. So another example that we have is as follows. So given the function h of xy, which is defined to be root of y squared minus x4, determine the domain of h and sketch it. So that's what we want now. We want to find the domain of this and sketch that domain. So how do we deal with that? So again, we see there is the presence of a square root, and we know already what that means. So we know that y squared minus x4 must be greater or equal to 0 for us to get outputs. You see, so that's what we know. We know that y squared minus x4 must be greater than 0 for us to get output. So therefore, we can immediately see that the domain that we're looking for, the domain of f, it is just all points x, y, elements of r squared, such that y squared is greater than x4, like that. So this is what we obtain. But now we want to sketch it. You see that? We want to sketch it like that. That's one thing that you want to see. But again, before I move on, there is another way again that you have to realize about this domain. You see that? Or so one thing that you have to realize is this. So for example, remember, if y squared minus 4 is greater or equal to 0, it simply implies that y minus x squared and y plus x squared is greater or equal to 0. That's one thing that we can see, you see. And we know that these two factors, they can only satisfy this condition if both of them, they have the same sign. So it means both of them, they can either be positive or both of them can either be negative, you see. So therefore, the domain of f can also be written as all points xy, elements of r squared, such that y minus x squared is greater or equal to 0, and also y plus x squared is greater or equal to 0. Union all points xy, elements of r squared, such that y minus x squared is less than or equal to 0, and y plus x squared is less than or equal to 0, like that. So this is another way of actually writing the same thing, you see, because we know that for these two factors to be positive, both have to have the same sign at the same time. But now, let's say now we want to sketch that. So how can we sketch that? How can we sketch that? So to sketch this function, we can make use of what do we call this? To sketch this function, we can make use of this second version of the domain, because this one, it carries a curve that can give us a hard time in sketching. Y squared is equal to x4 is something which is very hard to sketch. But if we were to look at all these other curves that we have here, then we can see that it is easy to realize that y is equal to x squared or y is equal to minus x squared. They are curves that we already know how they look like. So it's easy then to use this solution that we have here as our domain, you see. So now, let's see now how we can sketch these two domains that we have here. So to sketch then the two domains that we have here, let's create a Cartesian plane and see. So we can see that everything that we have here on the inside, it features the curves y is equal to x squared and y is equal to minus x squared. So I will draw them in bold line because also points along them, they can be taken. So I'll draw these like that. Like that. And then now we look. So what does the first point then suggest? So if you look at the first set, which involves these being greater than 0, what does that tell us? You see that? What does that tell us? So we need those two conditions to hold at the same time. So for which regions do we have for which these two hold at the same time? So first, let's ask ourselves, you see that? So if we were only to consider y minus x squared greater than 0, what region is that? You see? So if you are to look closely, you will see that the region y minus x squared greater than 0 corresponds to the region where y is greater than x squared. And that region, if we are to shade it, it is actually this region. So let me label this. So remember, this function is y is equal to x squared, and this one is y is equal to minus x squared, like that, you see. So we can see now that we have these two regions. So first, we want to find an intersection of these two regions, this region and this region. We want to find their intersection. So let's see now how to find their intersection. So first, I look for the region that satisfies the first inequality, that is y minus x squared is greater than 0, meaning y is greater than x squared. This is the region. that is being referred to in this problem. You see, so if I were to shade it, this is the region. It is the region that is contained within this zone. So it is the region that is contained within here, like that. You see. Then the next thing that we want is to look at the region that satisfies the second inequality. So we want the region which satisfies y plus x squared is greater than 0. So you will see that now if you are to look at this other region that they are referring to, then the region that we are talking about is the whole region that is outside and above this curve. So the whole region that is outside and above this curve is the region that we are referring to. So it is that whole thing here, 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 here. So it is that region, if we were to say, you see. So one thing that we now need is, where do those two regions intersect? So the region that we drew previously and the region that we drew next, where do they intersect? You will see that the intersection of this region is actually residing in this interior. It resides here in this interior, like that. So which means now we can actually sketch our regions and see what we obtain from that. So we see now that the final solution then, if we were to sketch our region that contains our solution, it is this region. Like that. So if you have to do the same thing again, you will see that the other region that you need also is this one. If you are to consider the second set, the other region will become like this. So this is how you find the domains of these functions. But again, I want to redo this problem using another trick that one can use mostly, which is directly linked to the procedures that you already know. So let's recall, remember, we want to find the domain of fxy is equal to y squared minus x4. We want to find the domain and sketch it. So we know that y squared minus x4 must always be greater or equal to 0. So this implies in some way y squared, y minus x squared, y plus x squared must be greater than 0 for all x. So if again I'm interested in knowing exactly what my domain is, I just have to proceed as follows. So to know my domain, what I'm going to do is I'm going to find the critical values of y. So what are the critical values of y? So if you are to solve here, you will see that the critical values of y are minus x squared and x squared. So what I'm going to do now is, I know that having two critical values suggests three regions. So there is the regions for which y is less than negative x squared, and there is a region for which y is greater or equal to negative x squared, but less than or equal to x squared, and y greater or equal to x squared, like that. So what I'm going to do now is I'm going to consider this region, and then I'm going to take any value of y that I can think of which is greater than x squared. So I see that if I take any value of y that is greater than x squared, this bracket is going to be positive, and this one also is going to be positive, so the overall line sign will be positive. So again, I know that if this sign is positive here, this sign has to be negative, and this one has to be positive, like that. So now I have to see which of these things carry the solution that I'm looking for. So we see that the inequality suggests that we need positive regions. So for which regions is positive that we're looking for? So we see that we have two positive regions in this place. You see. So which means the other way we can actually state the same domain is to say, therefore, the domain of f is actually every point x, y element of R squared, such that y is less than negative x squared, or y is greater than x squared. So this also suggests the same domain. And actually, having this domain, it makes even sketching much easier. Suppose now that I want to sketch this domain, how will I sketch it? So already I see that I have two restrictions. So first I'll sketch my restrictions, and my restrictions go as follows. So I have x squared and minus x squared. So these are the two curves that I have. So I have y is equals to x squared and y is equals to minus x squared. So we see that the first condition says that y must be everything below negative x squared, which means it suggests this region. And then the other one says y must be above, so which means it suggests also this region. So approaching this problem this way, it actually makes finding the regions much more simple and straightforward. So this is a nice trick to do every time when you have equations of this structure, you see. So yeah, this is how we find all these things. Then again, we have another example. So next example that we have is given pxy equals to ln 1 minus x squared plus ln 1 minus y squared. Determine the domain of px and sketch it. So again, we have this problem where we want to find the domain of this function and sketch it. So solution now. So remember, all the time when the trick to find the domain is to see spot fractions that you know it has obvious restrictions. So already we see now that here we have two natural logarithms, and we know that they can only accept arguments that are both non-negative or strictly positive, you see. So we know that from that reasoning, 1 minus x squared must be greater than 0, and y minus y squared must also be greater than 0. So we know that these two, they have to hold true at the same time. So now, if 1 minus x squared is greater than 0, then what do we know? We know that 1 minus x, 1 plus x must be greater than 0. And we see now that the critical values are what? X is equals to plus or minus 1. So having these critical values suggests three regions to explore. So we have the region greater than minus 1, less than 1. We have the region x less than minus 1, and x greater than 1. So if we take anything greater than 1, we see the first bracket is negative, while the other one is positive. So we have a negative sign here. This gives us a positive, this gives us a negative, you see. So we see that now this inequality is true in this region, because that's where we have a positive sign. So therefore, we can conclude and say, therefore, x must be an element from negative 1 to 1. You see that? And similarly, and we can see that similarly, also y must be an element from negative 1 to 1, like that. So that's one thing that we see definitely, that because both x equation of the x and the y, that y have the same structure, so they have to give us the same solution. So this implies the domain of f that we're looking for is made up of all xy points in R squared, such that x is an element from minus 1 to 1, and y also is an element from minus 1 to y as well, you see. So now how do we sketch this region? So to sketch this is how we proceed. So we have y, x, then 0. So in the x, we only take minus 1 to 1. So this is this region. So we take only minus 1 to 1. In the y again, we take minus 1 to 1. So this is this region. So it means now the region that is common or that is shared, it is this rectangular area here. That's the region that consists of all the values that can give us outputs when we put them onto that function, and therefore that's the domain. So this is the domain of f that you are looking for, like that. So yeah, this is how one gets to find the domain of all these different types of functions, you see. So it's good to practice and know how to play around with all these type of problems all the time. Okay, so many more examples, because we have to perfect our understanding on how to find these domains. So we have to look at all different variations of problems that are quite common. So given the function h of xy, which is defined as ln of 1 minus x squared, 1 minus y squared, determine the domain and sketch it. So now we want to find the domain and sketch it. So how do we go about this one? So to go about this problem, there is one thing that most people mistake that they always make. Most people, they always rush to say, they always think ln of AB is always equal to ln of A plus ln of B. You see? So this is something which is very dangerous, because let's check something. Let's say maybe I have ln of 6. This is the same as saying ln of 2 plus ln of 3, which is the same thing as saying ln of minus 2 minus 3. So this is not equal to ln of minus 2 plus ln of minus 3, because ln of minus 2 is undefined and ln of minus 3 is undefined. So do not always jump to use this law, because a problem like this one, people, they always make that mistake of strictly jumping to use that argument, you see. So so this thing is not necessarily equal. So let me just write it like that, to mean not necessarily equal. So this can only work if A and B are both greater than 0. That's when it's true. You see that? So if I want to add an extra condition, is to say that both A and B are strictly greater than 0. That's when this is true. Otherwise, if you don't know what your A is the sign of your A and what is the sign of your B, you can't really jump to make such a conclusion. So you can't do that. So which means if your idea was to actually try doing that, then you would have missed it already. So which means now we have to find ways on how we can actually find that domain without having to do all this stuff. So to do that, first we will check and apply the restriction that we know. So what do we know from our restriction? So we know that from the fact that the natural log checks only things that are greater than 0, we know that 1 minus x squared and 1 minus y squared must strictly be greater than 0. That's one thing that we know, you see. That's one thing that we know. So now how can we deal with this? So we see now that here we have critical values, which are what? So we see that we have two critical values, x plus or minus 1, and also y is equal to plus or minus 1. So all these things are our critical values for our inequalities. So now how can we deal with all this stuff that we have here? You see? So in order for you to see now the intervals for which this expression is always strictly greater than 0, we have to consider a cross between x and y. And how we consider a cross between x and y is done as follows. So what I'm going to do now, I'm going to construct some sort of a table of critical values which considers all different possibility crosses between x and y. like this. You see, so I know that x is reaching less than -1, and x is greater than -1, less than 1, and x greater than 1. And also I know that y is less than -1, and also y can be less than -1, less than 1, and y greater than 1, like that. So what I want to study now is I want to study the crosses between all these different regions for x and the different intervals for y. I want to see those intervals for which, when I extract values of x and y that satisfy them, I get positive results afterwards. So the first thing, I'm going to look first into this region. You see, so I'm going to look first into this region. And to look first what is happening into this region, I'm going to take first any value that satisfies this inequality and any that satisfies that. So maybe for x, I'll take -3, and for y, I'll take -5. Then what I'm going to do, I'm going to plug these there and there. So I see that because of the square, I will have one separating a big thing and one separating. So I'll have a negative bracket and a negative, which will multiply to give me a positive bracket, like that. You see. Then I also do the same thing between x, between -1 and 1, and still keeping y less than -1. So I take -3 for y, and x I take maybe 0.5. So I see that when x is less than 1, one bracket is positive, the other one is negative. So I have a negative product. Then again, I take values of x greater than 1 and those less than -1. So if x is greater than 1, the bracket 1 minus x squared is negative, and also y is negative. So I have a positive, like that. So once you know signs, any of these signs, you don't need to work hard to establish the signs of all the other regions, because the signs alternate. So since here we have a positive, the next has to be a negative, and here a positive, and here positive, here negative, and here negative, here positive. So you can't have two signs similar coming next to each other. That's how these sign tables, they are like in structure all the time. So which means now I can see that all the intervals that I'm looking for that have the sign that I need is this one, this one, this one, this one, and that one. So which means now to write down your domain of this function, you can write it as a union of all these things. You see that? So you can write it as a union of all these things. So you can come and say, what is the domain of f? So the domain of f first is all xy element of real numbers such that what? So the first region, x and y are both less than -1. So you will say x less than -1, y less than -1. Then union what? So union the second region is xy element of r squared such that what? So we see in the second region that x is greater than 1, but y is less than -1. So x is greater than y, but y is less than -1. Union, again, we do the same thing. So it's xy element of real square self, that's what? So we see in the other interval, x is between -1 and y, and also y lies in the same region. So we have x greater than -1, less than 1, and y greater than -1, less than 1. Union xy element of real numbers such that what? So the other region, so we are done. So now we go to this one, y greater than 1 and x less than -1. So x is less than -1, while y is greater than 1, and union xy elements of real numbers such that what? So we see the last region, x is greater than 1 and y is greater than 1. So we have x greater than 1, x greater than 1. So this is our domain, like that. You see. So it is a union of all these regions, these 5 regions that we have managed to find. So if we were to sketch it now, how do we sketch that? So to sketch it, this is how we proceed. So for x, we see that x has critical values -1 and 1, which we'll label. So actually now it's strictly greater than. Is it strictly? So yeah, you have to draw dotted lines. So these are our regions of interest. Then for y again, so if you are to study carefully, you will see that all the regions that are mentioned in this domain, we have this one first. This is the part of the required domain. And also we have that one, which is part of the required domain. Also we have this one, which is part of the required domain as well. And then we have this one, which is part of the required domain, and that one, which is part of the required domain again. So these are the domains of this function. So if they say find the domain of a particular two-dimensional function, this is the procedure, but we have seen that it always works differently or with different types of functions. But the main goal is always to realize the restriction that applies to a particular function, that's your starting point, on how you can actually get the domain. So then you can then see how to go from there to there. So all these problems, they've kind of like demonstrated how to look at the idea of finding the domain of two-dimensional function. And the same strategies can also be implemented for functions of 3 variables. So yeah, guys, thanks for watching. See you on the next lesson.